All right, I think it's time to get started. Welcome back. So we do have homework due tomorrow. Check it out. And we'll have our quiz as usual on Friday. I have one more little thing to say about grammars, and then we're going to go on to the next thing, which is another type of machine. So one last thing I wanted to say about grammars is that real-world programming languages are based on grammars, typically. Real-world programming languages have grammars. And I thought it might be nice to look at one in particular. And what I would like to look at just for a few moments is the official published grammar for the Python programming language, which I think most of you have some familiarity with Python. And I have it right here. Come on. Figured out how to embed a web browser right inside my scribbly thing. So if you're interested, you can see the link at the top there. You probably can't read that. I'm going to post it on our class website. But this is the official Python reference documents, which you can read online. The official description of what Python is. This is the purpose of the grammar, actually. I don't know if you've ever tried to think sort of philosophically about, like, what really is Python, the programming language? What is it? Well, it's a programming language. Like specifically, what is it? I guess the answer to the question, what is it as a language, has to do with what programs are correct in Python versus what programs don't make any sense in Python. This is the only sense I can make about the question, what exactly is Python? What you're asking, I think, is, how do you tell if something is valid in a Python code or if it is invalid? And one answer to that is just like, well, if I hit the button and I get an error, then it must have not been real Python. But if I didn't get an error, then it must have actually been real Python. Python, though, as most programming languages, Python is sort of an open source programming language. That means nobody actually owns it. And anybody who wants to can make their own Python interpreter. So to say Python is, as a language, it is just whatever things do not give you an error when you hit the button. That's not actually a very good definition, because it fixes the definition of the language is fixed to a particular interpreter or compiler for the language. And typically you don't want that. Like, the language should have some kind of existence, even apart from which interpreter you're using, which compiler you're using. So, in fact, the language of Python is defined by this grammar and a few other sort of rules about how it works. So there are abstract descriptions of Python. And typically when programming languages are created, I don't know how typical this is, but nowadays at least, if someone decides they're going to make up a new programming language, usually they would define the grammar for it, define how it works before they ever write any kind of compiler for it, right? So anyway, all this to say, there is an official grammar for Python, and it's important, and I just wanted to look a little bit at it. So it's very long, first of all, much longer than the typical grammars that we use in this class. Come on now, I'm trying to scroll here. Oh, I know. Yeah, okay. So here is the language, or the grammar. It's they call this PEG grammar. I don't know what that stands for. I think the G stands for grammar. But this is a particular way of writing. When we write grammars, we typically write like, S goes to AX, X goes to BY, that kind of thing. So the notation that's used in this grammar document is like this. S colon, it would be written this way. So you're not going to see any arrows over here. You're going to see a bunch of colons. But that's not a big deal, right? You can handle that. Come on now. I'm not used to... Stop. I'm not used to scrolling with this thing. There we go. But now it's little. Okay. It's going to be worth it. So here you have, for instance, you can see something like assignment or augmented assignment. Is that big enough? Maybe not. If you know Python, you know there are these operations like the plus equal. They call this augmented assignment. It's a way of giving a value to something but also changing that value at the same time. That's what the plus equal does. And these other things, the times equal, I know. I actually don't. I know Python, but I'm not a super expert. I don't really know what these things do. Does anybody know what these are? There's some fancy stuff. I've never seen those before. Anyway, oh. Yes, I can scroll. No. I'm going to scroll inside the box. Nope. Sorry. There we go. All right. I wanted to look particularly at something that I do recognize from Python. Even if I know some of you don't know Python, it's not a big deal. I want to look for something called a function definition, function def raw. So right here you will see what is a function def raw. This is a raw function definition. And it says, the colon here, this bar means the same like we say bar in our grammars, it means or. So function def raw, it can look like this or it can look like this. But let's look at the first one. First of all, it says def. All right, so this is what this means. I want to just try and trace out the meaning of just this little part of the grammar. A function definition in Python, even if you don't know Python, I'm about to tell you. A function definition looks something like this. Def square of x, then you put a colon, then you indent and you say, I'm going to do this maybe like this. Of course, if you were really writing this function in Python, you wouldn't write it exactly. You'd probably just say return x times x. But just to make it look more interesting, I'm going to do it this way. So what we see here is a definition in Python begins with this special word def. And that appears in the grammar right there. Def, right? And then followed by a name. That's what this is. That name in uppercase is not a specific thing. It means anything which you can plug in whatever string you want. Or not any legal string. Not every string in Python is allowed. But and then you see a parentheses, a left-hand parentheses right here. That's this. And then you see a list of parameters, which are variable names. That's what you see right there. And then you see the closed parentheses, which is there. And then you see this thing here in brackets is an optional argument that you're allowed to put in. And actually, I don't know what that does in Python. Apparently, you can put an arrow right here. Does anybody know what that is? I've never seen that in a real Python. But anyway, this is optional, which I left it out. And then you see the colon, right? I'll put a little green circle around that. That's right there. Okay, so the line in the grammar is actually describing exactly what kinds of things you're supposed to put in a raw function definition. And then after the colon comes, I gotta practice scrolling. Oh, those things don't move with it. Sorry, it's gonna look crazy. But anyway, some more optional stuff, followed by block. Now, block is another grammar thing. So I'm going to look up in my grammar, what does block mean? Well, okay, I got to look for block now. Parameters. Here's a definition of what parameters means. I think it's down here. Block. All right, what is block? Block consists of new line. Okay, that means from here, you go to the next line. All right, followed by indent. That means this. You go up one level. As you know, Python indentation is important. And then statements. So these statements refer to all this block of stuff that I said here. And elsewhere in the grammar, you can look up exactly what is allowed for a statement. We don't need to get into it. And then this thing, dedent. That's when you go back, when you unindent. The word for that is dedent. All right? But anyway, I'm just trying to show you what a real-life grammar for a real-life programming language looks like. It is quite complicated, and I would say for an ordinary Python user, like me, for example, I don't have to understand most of the grammar. Like I have an understanding basically of, I mean, this right here, I feel like I understand everything about the structure of this part right here, or the grammar of this part. There are other things that I don't understand so well, and you can use the language fine without ever thinking about the grammar really, but the grammar is important if you are interested in, say, if you wanted to make your own Python interpreter or something like that, you definitely need to understand how the grammar works. All right? So we're not going to say much more about this. I just thought it would be nice to see a real example. Anybody have any questions about this? Excellent. All right, then I think we can move along from grammars. So we're going to talk about grammars every so often as we go, but for now at least, I'm done with that. All right. Great. Let's talk about another type of machine. So for the next few times, we are going to talk about what our book calls stack machines. By the way, happy Pi Day. I hope you all had a good Pi Day. It's a shame we couldn't have some kind of math department Pi Day event, which we usually do. But I made meat pies for dinner and a strawberry rhubarb pie for dessert. It was good. I'm hoping to have a piece of that strawberry rhubarb pie when I get home today. I'm looking forward to that. Okay, so a stack machine. This is yet another kind of machine for accepting or rejecting strings. But actually, it doesn't look like an NFA or DFA. It doesn't have a diagram, really. But let me just say, this machine, it kind of has states, maybe. It sort of has one state which can change and take many different forms. I'm going to say this machine uses a stack for memory. And if you've taken some kind of data structures class and talked about stacks, this is that kind of stack. So it's a memory structure in which you can access sort of all the elements lie in a line or like in a stack, and you're only allowed to access the one at the front of the line at any given time. This is called a stack in computer science. If you never heard of that, that's fine. I'm about to explain it. The idea is there is a string, so the string is processed one letter at a time by the machine, just like in an NFA or DFA. The string is, I'll say, read one letter at a time, from left to right, as always. And, in an NFA or DFA, depending on which letter you read, you can jump to a different state. In a stack machine, there aren't states, there's just a stack, and the stack can change over time. So each letter can change the stack. All right? And so as you go, the stack changes from one step to the next. But the stack can exist in many different configurations, and in fact there are infinitely many possible things that the stack could be. And so in this way it's more powerful than NFA or DFA because there are only finitely many states in NFA or DFA. But the stack can be in infinitely many, in theory, different configurations. All right. Each letter can change the stack, I'll just say, according to specific rules, and the rules determine the behavior of the machine. So if you want to describe to me a stack machine, what you have to tell me is, depending on which letter you see, how does this letter change the stack? How does this other letter change the stack? That's how we're going to describe the machine. So you actually don't have, there's no kind of diagram for it. It's just a list of rules that you use to describe the machine. So each letter can change the stack according to specific rules. And those rules are the machine. Those rules describe the machine. There's no diagram that goes along with it. All right? What happened? I think I jiggled the wire. All right. No problem. Okay, let me just describe the stack a little bit. The stack is like a stack of papers or something. You imagine it has a bunch of stuff sort of stacked on top of each other. So one way you could draw a stack is like this. And let's say it has these letters in it, A, B, C, D. D is on the top of the stack. And the way that a stack works is you can only access the thing on the top of a stack. That's why it's called this. You should imagine it like a stack of papers where if you want to get at one of the things that's down below, you have to move the top stuff out of the way first. All right, that's how a stack works. And there are really, there's only sort of two things you're allowed to do with the stack. You can remove something from the top of it, or you can stick a new thing onto the top of it. You're not allowed to reach into the middle of it. So those operations, they have cutesy little names. So one thing I'm allowed to do would be to remove the thing from the top. This is referred to as popping the stack. Pop. Pop means the thing on top sort of flies away, right? So the language that's used here is pop, D. P-O-P. I popped the D off the top of the stack, and now the D is gone, all right? I'm not making this up. This is how people talk about stacks. People who wear suits to work still say this, all right? And the other thing you're allowed to do is put a new thing onto the top of the stack. That's called push. So if I were to pop the D and then say push a X, now the stack looks like this, right? You are only allowed to put things on the top of the stack. There's certain operations which are easy to do with a stack. Some things are quite difficult to do with a stack. For instance, if you want to reverse the order of the elements in a stack, it takes a lot of steps. You've got to pop everything up the top until it basically you run through the whole thing, and then you push everything back on in the reverse order. All right. This is one way that you can store things in order in a computer. There are many other strategies for storing things in order. This works well for certain types of things. It works pretty badly for certain other types of things. If you're interested in learning about that sort of stuff, you should take the data structures class. There's a class called data structures, right? Yeah, that's in the computer science department. It's about that kind of thing, all right? In most programming languages, they just have something called like a list or maybe an array, and they don't typically work like stacks. You can use any of the elements anywhere you like. Anyway, this is the terminology for a stack. Now, we are never going to write them like this. This is very cumbersome to write them in these little towers like this. More commonly, we will write them just as if they looked like strings, where the top of the stack is on the left. So we are going to write our stacks like this. So here I popped the D, and here I push an X. Ooh. Right? So the left side of the stack is the sort of like the top or the front of it. All the action happens on the left side when we write stacks in this way. All right? Excellent. So I'm going to try to describe a stack machine. All right, here's a very simple example of a stack machine. Remember, the whole machine, it doesn't have a diagram or anything. It just has some rules. And we're always going to describe it sort of in 3 columns. Here's the first rule. So this is like rule number 1. Sometimes we'll give them numbers if you want to refer specifically to them. Rule number 1 in my stack machine says read A, pop S, push SX. What that means is from the input string, if you read the letter A, you are allowed to pop S off the top of the stack and push SX back onto the top of the stack. All right? You always only pop one letter at a time, but you can push more than one letter at a time. That's just how the machines work. Okay? So what this means is I can read the letter A. This will pop S, and then push SX, all right, onto the stack. Okay, let me just describe to you the other rules, and then we'll try and talk about what kinds of strings are accepted or rejected according to these rules. All right, epsilon, as always, means the empty string. So these are the rules. If you read A, you can pop S and push SX. If you read B, and there's an X on the top of the stack, you can pop that and push nothing. And also there's this special rule. Rule 3 says at any time you can read nothing, pop the S, and push nothing. All right? And let me just describe to you how, these are the rules for the machine. How do we say if something is accepted or rejected or whatever? The stack always starts with what's called the starting stack symbol, which is basically always going to be S. It will be called S. So the stack begins with just S by itself. And a string is accepted if we can read the whole string doing the rules to change the stack. So we can read it fully, doing the appropriate, I'll say, pops and pushes, and end with an empty stack. So this is what determines if a string is accepted or rejected. If you can read the whole string and end up with the stack being empty, then it's accepted. And if there's no way to do that, then it is rejected. All right? This is how a stack machine works. So let's try, in this example that I did up there, I want to know, is this string accepted or rejected? Let's try A, B, B. Is it accepted or rejected? So what you have to do, this is a little tricky to write down the steps, but you have to imagine reading this string one letter at a time, and you have to think about what the stack looks like as you proceed down the string. So I'm going to write this. Actually, there's another way that we're going to write this in a moment, but just to get us going here, I'm going to do it over here so we can still see the rules. We begin with A, B, B, and S on the stack, right? This is how we start. Just because I said you always start with the stack being just S. And I'm going to try to read the string one letter at a time, doing the appropriate operations. So first of all, I'm going to do rule 1, because rule 1 is the only thing you can do if you read A, right? So I'm going to read the first A, and changes the stack. So the way I'm going to indicate that is I'll write A, B, B, but I'll sort of cross off the first A to indicate in this step, I just read the first A. And what happens to the stack? The S is on top of the stack. You pop it off, so throw away that S, and then push back on SX. It looks like this. You throw away the S, and you replace it with SX. All right? And that was the first step. If you like, I'll say this is, what I did in that step was rule number 1, just to clarify. We're not always going to write out the rules, because once you know what you're doing, it's not so hard to tell. Okay. All right, next I'm going to read the next A. So in the next step, I will cross off the first 2 A's. And now, what happens to the stack this time? The S on the front is popped off and replaced with SX. So what's the stack going to look like now? SXX, I believe, right? It used to have this S here. This S gets thrown away and replaced with SX. So now it says SXX, right? And that was rule number 1 again. All right. How do we proceed? The next letter is a B. Now, you will notice, if you look at the rules, when you read B, you have to pop X. But that's not valid right here. You're not allowed to do that. because when we pop things, they have to come off the front of the stack. That is the left end when I write it this way. And there is no X on the front of the stack here. So actually, it is not allowed to do rule 2 at this point. We can't do rule 1, because that requires reading an A. You can do rule 3, though. Rule 3 is an epsilon read. So this means you don't read anything, but you pop the S, and you replace it with nothing. And so this is what I'm going to do in this step, because it's the only possible thing I can do. My input string, I did not read anymore. This is what read epsilon means. It means you don't actually read any letter. I pop the S and replace it with nothing. And so the stack becomes just XX. That was rule number 3 that I just did. All right. Now we can proceed with rule number 2, right? Number 2 says read B and pop X. So I'm going to do rule 2 once, reads the next B, pops X and replaces it with epsilon. So that just gets rid of that X, right? Throw the X away and replace it with nothing. And then I'm going to do another rule 2 to finish it off, right? To read the final B, I do rule 2 again. I pop X and replace it with nothing, so the stack is now empty. And so that string is accepted because I ended up, remember I said, a string is accepted if you can do all the stuff, read the whole string, and end up with an empty stack. So So, come on now. Oh, okay. I see the problem. Sorry. So B is accepted. All right. Yeah.
Why did you do
So at this point, the next letter to be read was a B. So you might think number 2 is the way to go, but number 2 requires that you pop X. And remember, since the way the stack works, you can only pop things on the left side, which is the top of the stack. And so at this point, it was not legal to do rule 2 because there's no X on the front of the stack at that point. Does that make sense? Yeah. As usual, we're going to have to get used to thinking about things in terms of stack machines. In my opinion, they're a little trickier to think about than NFA, DFAs, but we get used to it. Can we try it on the same machine? Let's see an example of something which is not accepted. How about, maybe I'll do it over here. I just don't want to scroll past the machine. Let's try AB. This one turns out is going to be rejected. But let's see what we can do. So I'm going to make a little chart again. So we begin our input AB. The stack begins with S. This is always how you start, with S on the stack. Okay, what can we do? Well, I can do rule number 1. In fact, rule number 1, well, I could do rule number 3 at the first step, but you shouldn't do that. That will kill the stack, and then you won't be able to go anywhere else. So I'm going to do rule number 1. The stack now becomes SX. This was rule 1. Right? What next? Well, I can't do rule 1 at this point because I'm not reading an A. I can't do rule 2 at this point because the top of the stack is not X. You can't pop X. So my only choice is to do number 3 at this point, right? We must do rule number 3 just because there's no other option. Rule 3 does not read a letter. It does pop the S and replace it with nothing. So this was rule number 3. I didn't really like that one, but it's the only possible move you can do. All right. Can we continue? Yeah, actually, we can do rule 2 at this point. So that will read the B, pop the X, and replace it with nothing. This was rule number 2. Somebody in the Zoom just sneezed. And then somebody else said, bless you. They're so kind to each other. All right. And I think at this point, we're stuck, right? There is no way to proceed. None of the 3 steps here is legal at this point. I have to read an A is the next thing to do, but I can't do rule 1 because that requires a pop S. I can't do rule 2 because that's reading a B. And I can't do rule 3 because that also requires a pop S. So here we're stuck. That means it is impossible to get to the empty stack using this string. And so that string is rejected. So I'll just say we cannot read A, B, A, B, and end with an empty stack. So A, B, A, B is rejected. This is how a stack machine works. All right. Now you should wonder, maybe I could have made different choices and somehow gotten it to be accepted. That might be possible in some examples, but in this case, there wasn't any other way that we could have done this. We could have done rule 3 at the very beginning, but then we would immediately be stuck at that point. So any choice of sequence of moves will make you get stuck. All right. We are typically going to write these out in a slightly different way. So rather than these little charts every time, there's a more compact notation that we're going to use here. So a fancier, or not much fancier, but a better notation for A, B, B. Let's do that one again. But I'm not going to write it in the same way that I did before, which is a little cumbersome to write those big charts every time. Here's how we write this, or here's how this is written in our book at least. What you have to keep track of in every step is just what the word is, what the string is, followed by what the stack is, right? And so we're just going to write those as pairs every time, and then they use this arrow. I think the author of our book is like obsessed with different kinds of arrows. So when he's doing stack derivations, he uses this arrow with the little post on the left end, which is different from the arrow without the post, which is used in grammars. Double arrows used in grammar derivations. In the stack machine derivations, he uses this one with the bar on the side. Okay, anyway, here's the way we write this. So you will notice, so that right there is the first 2 steps. I hope that you can still see this up here. We start with A, A, B, B, and S on the stack. That's this. And then the next step, I just put A, B, B, and S, X. Actually, when you're doing this, you don't really care about listing out the letters that you've already read through, right? All that matters is the letters that remain when you're trying to, the ones you have to read next, okay? And sometimes, for clarity, they put a little 1 here. That indicates that I was using rule 1 in that step. This is the number of which rule you used. Okay. The next step would be another 1 because I used rule 1 again. This time it says BBSXX, right? I'm just trying to follow the same steps here, but writing them in a different way. Okay. Next is rule 3. And it should say BBXX. Right? I'm just copying the same stuff. Next, I used rule 2. What's the pair going to look like in the next step? B comma X, yeah. BX. Then I did rule 2 again, and I get epsilon, epsilon, and that means it's accepted. So the goal when you're writing it in this way, what you're trying to get to is epsilon comma epsilon. And that indicates that the string is accepted. So when you see that, you smile when you see epsilon comma epsilon. That means it is accepted. So the game is, if you can get it down to epsilon epsilon, then it's accepted. And if it's not possible to do that, then it's rejected. All right? These pairs, when you see this in the book, each pair like this, let me just write specifically, it is the what you see first is the remaining letters, comma, the current stack. Right? And the book uses a name for this. A pair like this, this is called an instantaneous description of the stack machine, also known as ID. So these pairs are referred to as IDs in our book. An instantaneous description. It tells you, this is kind of like a state for the machine. It's at this moment, what's on the stack and what am I looking at for the string, right? That's called an instantaneous description. And of course, the big question on stack machines that we talk about, just like all of our other machines, what is the set of strings that are accepted or rejected by this or that machine, right? So our example that we've been looking at all along, let me just write it again. Just so A was pop S, push X. B was pop X, push epsilon, and then there was a epsilon S epsilon, right? Anybody have a feel for what kinds of strings will be accepted by this this machine? We saw AABB was accepted. ABAB was rejected. Yeah.
Maybe A to the N, B to the N.
Yeah, he said maybe A to the N, B to the N. Actually, that is the language of this stack machine. So in this case, the language accepted is A to the N, B to the N. Can you say any words about why you think that's right, or just a hunch?
Well, the first string we used was AABB, and then when we mixed up the ordering of the A's and the B's, it was rejected. So
Yeah, I mean, AABB seemed to work. Yeah. Yeah, so actually, in this example, they must be the same number of A's and B's. The way that, sorry, I wrote the rule wrong. It should be push SX right there. Yeah, in this case, you do need the A's and the B's to be the same number. The way that I would think of this is, as you are, like, look at these IDs. Check it out. I would say, when I'm reading this, it kind of boils down, or I could break down this procedure into sort of two blocks of time here. Sort of this, the first era, the first age in which S is on the front of the stack. What you're doing here is you're reading A's off the front of the word, or of the string, and every one of these A's is kind of being translated into an X, right? That's sort of the effect of these steps at the beginning. You are, as long as the S is on the front, you can do that rule number one, and it gets rid of an A and inserts an X every time. And what are these steps doing? Well, after you clear away the S, these steps are reading B's and clearing X's away at the same time, all right? So I had two A's at the beginning, which caused two X's to appear. And then I read two B's at the end, which cause two X's to disappear. And I end up with epsilon, comma, epsilon. If you think of it in that way, I think you will agree the number of B's must equal the number of A's, or else either you will have some X's left over if there aren't enough B's, or if you have too many B's, you'll have some B's left over, and the stack will be empty, and you'll get stuck that way, all right? So this is why, yeah, you need the same number of A's and B's. And the A's have to come before the B's, because if the B's are first, when S is on the front of the stack, if you have a B, then you'll get stuck immediately, and you won't be able to do anything. So it's a little tricky to decide what the language is, but this is how we do it. All right? Any other questions? I got another example. I mean, I got more than one example, but probably for today, we can just do one more example. How about, so this is a new one. Okay, these stack machines, we're always going to write them this way. The old read, pop, push. ASX BXY, BYS, and epsilon S epsilon. So I have 4 rules for this one. You know, in the previous example, the stack just uses X and S. Here I have S and X and Y on the stack. All right, I would like to try to say what the language of this stack machine is. Maybe we'll just try a few example strings. So let's try ABB. So I'm going to write it this way, using IDs, ABBS. Now you are going to have some choices in each step. You know, there's typically more than one option that you could possibly do. Anybody want to suggest which rule should I use here? You can show me the fingers if you want. Yes, the nice one finger, not the mean one. Yeah, rule number 1, all right? I'm going to read an A because A is at the beginning of the string. So I do rule number 1. What remains to be read from the string is just BB, and then the S, you pop the S and replace it with an X. So it now says BBX, right? Now, you could have done rule 4 at the beginning, right? That would have been legal, but it would have cleared the stack immediately, and then you'd be stuck. So don't do that. Don't. Generally speaking, you shouldn't wipe out the stack until you're really done. Okay, next I have 2 choices, rule 2 or rule 3, but actually rule 3 is not valid because I have to pop X. So I got to do rule 2, and it will now say B comma Y. And next, I guess I have to do rule 3. And now it will say epsilon comma S. Ordinarily, you might worry a little bit because I have ran through the whole string, but I have not yet exhausted the stack. But we have rule 4, which will clear the stack. And so rule 4 gets me to epsilon epsilon, which means this string is accepted. So ABB is accepted. All right. Let's try, any questions about that? Okay, how about, let's try AAB. What happens with that? AAB. All right, comma S, right? That's how we begin. Again, I'm going to start with rule 1. It now says AB, comma X. And now I'm stuck, right? I don't think you can continue from here. So this is stuck. You might say, well, maybe I shouldn't have done rule 1 at the beginning. Is there some other way I could have done it? Well, okay, I guess I could have done rule 4. That's the only other thing that we could do, right? In this case, it would say AAB, comma epsilon. And again, we're stuck, right? So there's nothing, no way that you can accept AAB. So AAB is rejected. All right. Can we try to get a sense for what kinds of strings are accepted or rejected with this language? I think it's a little, given those 2 examples, maybe it's not very clear just based on those 2 examples. One thing I would encourage you to notice is, in this example, the stack never grows, right? The stack is always, it's not just because of these strings I'm using, but the stack, every time you pop one of these guys, you push one of these guys again, except for this one, which happens at the end, right? The stack is always kind of occupied by one of these letters. It's always either S or X or Y, all right? Because you always pop one of them up, but then you push another one up. The stack never gets bigger than that. It never gets like 2 things on it. And it doesn't go down to 0 unless you do that rule 4. In such a stack machine, actually, we can think of this like an NFA. Because there's only 3 possibilities for the stack. It could be S, it could be X, it could be Y. That's it, right? And so we can think of it as an NFA with three states, S, X, and Y. Because these are the only values that are ever present on the stack, all right? Unlike the previous example, could have had things like SXX, right? But this example never does that. S, of course, we'll imagine to be the starting state. And then, in fact, the rules of this stack machine translate into rules for the NFA. So when I see read A, pop S, push X, that means this, right? If the stack says S and you read A, then after that step, the stack will say X. And if the stack says X, you read B, and after that, the stack will say Y. And that was the second rule. The third rule, if you read B and the stack says Y, it should say S again. And the fourth rule, how would you interpret the fourth rule on the NFA diagram? Yeah. Yeah, it means S is the accepting state. The fourth rule kind of means when you see S on the stack, you can be done if you want, right? That's how you should imagine the fourth rule. So that means S is the accepting state. All right. Now I think it becomes a little clearer. What is the language of this NFA? The strings which are accepted are just ones which go around and end up at S again. So the language here. Can anyone say that as a set or maybe as a regular expression or something like that? Yeah.
Parentheses, ABB, parentheses star.
Yeah, right. ABB star has a regular expression, or you could, if you prefer, it's basically the same. It's ABB to the power n. Right? This is not easy to decide just by looking at the stack rules, but you will notice in this case, so it is a fact, certain stack machines can be translated into NFAs. And then you can look at the NFA and decide what its language is. All right? I got a few more examples, but I think they can wait until next time, if that's all right. I got to get my piece of pie before my kids get home. If I eat the whole thing, they won't notice. All right. Homework is due tomorrow. I'll see you then.